think the last year, I think there are some conferences I organized, and now it will be very amazing. So I can explain how we can use map and combine with the AI. Actually, it gives some very successful applications in biology. Right? So in terms of Guo-Wei's view, this is actually revolutionized the biosciences. Okay. Now, so that's the background. And of course, this is people, a lot of people in today's conference use the geometric approach as well. So if we combine topology and geometry, they definitely give a lot of applications. Right? So now, as I said, I'm more interested to look at the possible, because I'm a topologist, so I look at the more possible new topological features. So I try to explain. Now there's one thing here. Next one I explain a bit. So it seems people, this is a new one, so-called path homology, introduced by Professor Yao. Seems it was introduced just recently, around 10 years ago, and the people maybe pay less attention on this new homology theory. So I will try to explain. So now, for path homology, as I said, mathematically, actually, they break through some frames, or I should say, the frames of a traditional algebraic topology. Okay, so that because if you look at this simplicial homology and if you look that, you see that there's a boundary operator need to be, for making boundary operator to be well defined, you get simplex, you need to alternating sum of its phases. Now the construction, when I say this breaks through the frame of the traditional algebra topology, in the sense that the path complex, it may not satisfy the condition that given a simplex, you have to take all possible phases. So in some cases, it will fail. These are missing phases come out. That's but the homology theory still works. That's an amazing point, you have to say. So I actually generalized the original homology. So there will be a lot of work in Yao's group. I actually started with maybe 10 years ago, and to look at this game. So be given like I think in beginning they look at the diagrams and try to get some topology, the geometry on the new topology and geometry on diagram. So that's why they introduced the path homology. Okay. Now, the briefly speaking, so the interesting part, at least in beginning, in your school, try to look at the given, say, diagram, right? So now you look at the possible paths, the usual sense. So you just like go steps from one vertex to another and keep going, right? Now, and from this way, you will get a complex. Like, so you look at all possible, say, two-dimensional complex, you think about all those passes go 3 steps, right? 3 nodes. So from node A, if your direction go to B, let's put in the 1, then continue. So put the direction to C, so you get 3 nodes. You think about this is a kind of like 2 simplex, like that way, and you get you collecting all these things together. And then you can follow the ideas of a simplicial complex, and you get some kind of change. So you add up all these possible passes with the same number of nodes, right? So you get the vector space. And now the key point that you try to define the boundary operators, so you try to introduce homology, and then you discovered that it's something's not easy to see, because there's the path, if you A to B to C, so you have a path, but you delete the middle node, say B, remove, maybe there's no path from A to C. So that means that there's some phase operator may not may not be defined. And the way I explain here that, well, there's some way when you take this path and try to think about the associated simplicial complex, the chain complex of there, and then the key point what my experience here is not exactly the same as what in the paper of yours group, but they are the same object. So for details they can explain. So what I explain here because try to coincide with what I call hypergraph homology next. So the way is that you get some groups which boundary operator may not be well defined. What do you need to do? Well, you can look at the chain complex there. So there's a smallest chain subcomplex and containing these groups passes. And that will be given. And also you can look at another way, actually in their paper, they defined another way, look at the largest chain subcomplex contained in this graded, by different graded vector space of there. And it turns out they are actually whatever you're doing, like what I call imp star, or the large chain subcomplex, or we take smallest chain complex containing these passages, they are in homology are same. So it naturally gives us a defined homology, so-called path homology. Okay. Now, so here's some. This just give a brief information how the path homology was introduced in homology in mathematics. Now, there are a lot of interesting applications now. I think nowadays, so you see there's quite recently there's some nice application. People pay attention for that for path homology and do give some applications. And I mentioned that actually also our group also give applications. I started recently to look at. There's some amazing application of the path homology, which can apply to biology and material sciences. In chemistry, actually, they can distinct the quadraticity, like the symmetry. That usual, so far, the topological approach is hard to distinct, but the path homology can, persistent path homology can successfully to distinct that. So it's quite useful now. Okay, now, so as I explained, I tried to look at the more mathematical methodology. So I still think about how this path homology can be moved to even more general situation. So there's one game is that when we try to look at the networks, of course, like given by graphs. So I'm thinking about a bit for graph data. So in the sense that we do not assume that we want to some people already defined distance there. Okay, so we just working on data that's naturally given by nodes and some edges there, right? And we try to look at the high dimensional structure over there. And for the networks beyond pairwise interactions, the simplicial complex can be a good model. And another more general model is will be use hypergraph, right? So let's essentially remove all possible constrained conditions. Just give a collection of subsets over there, and then you as a hyper edges. Now the question will be like whether we can introduce topology. Here, topology means you can introduce homology theory in a natural way, which can give some topological features on hypergraph. It turns out using follow the ideas of path homology, well, it works well for the hypergraph. So we can also introduce hypergraph homology in a natural way, which I say a bit more in mathematically. So you start with a hypergraph. So that's from our view, just like in abstract way. So you get a collection of finite sets, right? So then you can take a simplicial closure, so you get the smallest simplicial complex containing hypergraph. So there's some missing pieces we can fill in. Of course, people don't like say, oh, you are get simplicial complex that different hypergraph. I agree, no problem. This is the first step, but we have a next step. So next step, it means that if you just follow the idea of simplicial homology. So when you get a change, actually you get the linear combination of simplices, right? Hypergraph, you do the same way. You get the hyper edges, you take a linear combinations. So you think about this chain, but there's one thing, of course, is bad, is that it's hard to define the boundary operator. For simple complex, you can do that. Now, what we can do here? Well, you can do the bigger one. So I mean, simplicial closure, that's the simplicial complex. So you can introduce the chain complex as usual. Okay, that's for the simplicial complex up here. But then for those chains as given by linear combination coming from hyper edges, well, that gives just like a subspace of vector space up there, right? And now what you validate is you cannot define boundary operator. Now what do we need to do? Well, you look at all possible chain subcomplex. As I explained using the past homology idea, you look at the smallest like a chain subcomplex containing hyper edges. Yeah, you just move down. And then amazing thing is that, as I said, you look at the lower one. So those like vector space forms as a chain subcomplex, you move up to go up to the largest one. And of course, they are not equal, right? And important the same is that when we the important the same is that there what we call ink, right? And there's a small largest chain subcomplex contained the linear vector space given by linear combination of hyper edges, and the smallest chain complex containing all hyper edges. There's a natural inclusion there. They are induces isomorphism homology. So this gives a natural way to introduce the hypergraph homology. Exactly, that's what we did a few years ago. And so that's one thing. So and actually we found many applications of these hypergraph homology. So here I just take example. We can to work on these, the protein ligand, we can work on the protein ligand models and try to make applications out of this hypergraph. So the data running seems quite good. So somehow it's this gives us successful applications for these new topological features so obtained from hypergraph homology. Okay, so now in this report, I try to explain more, right? So what's going on next? Well, actually, there's some more well, I move to next one. Okay, so actually, exactly in previous talk, so there's something about the weight, right? So we have the data maybe have some weights. Now, how to handling the weights? That's actually the interesting point here, right? So, of course, you assume like now when I say data, I'm thinking about the graph. Okay, so nodes, the ages, so there's something over there. Okay, so we try to get some say topological features. Now, assuming there's something like weight over there, right? So then I found that there's some interesting things that actually is introduced by Professor Yao again. So one interesting thing is that assuming like each node, right? So you have a weight over there. So you assign some weight, and this is called that. Okay, put in the notation called that. And you look back about the simplicial homology. Okay, So the point is that if you use your simplicial homology, will be either homology or cohomology here. You will take alternating sum of this is the co-faces, right? Now, assuming like there's some weight over there. Now, if you take a weighted sum, so you remove this weight vertices, then you add the weight, this weight there, and then turns out it works. Still make a chain complex. Okay, so let's get some interesting. So they're like you're testing at least mathematically, right? It works. So this gives kind of like a so-called the dead homology already published, right? And then there'll be the game here is an example, like you're testing. So you look at homology will be the same game. So you look at the simplex. Okay, so here's simplex over here. So vertices labeled by V0, V1 up to Vn. And then the usual boundary operator. So you say you remove this Vi. Okay, so you get the, simplex is drop dimension by 1, and then take alternating sum, right? Without this sum. So assuming actually for any commutative ring, you are as a coefficient ring, so you put some number. So each vertex you just assign some number there, and then you make some put a weighted one, and turns out this law. So as a new boundary operator, it turns out this law works. So here's a testing game. You just say 3 V0, V1, 3 of them, right? Two simplex. So first the game, you put some numbers over here. So this is the weighted sum. And now keep this procedure again. So you take next step should be remove like this is V0. So you put some weight aside here, remove another one. Okay, V1, you put the weight here. And you can see that they are all canceled together. So it really gives make operator twice will be 0. That means that you get chain complex. So it works seems quite nice. Well, and then when I open these papers given by Professor Yao and his people in his group, and so I quite interested. So it reminds several things. So the first thing it reminds me that people actually have been working on the so-called weighted spiritual complex, actually backwards to 1990s. And then so there's a student of mine, actually now he of course he already graduated at NUS. So I asked him to work on this object. So actually he did a lot of work with Chengyuan Wu, right? He did a lot of work on this topic in his even very nice thesis. And now then we introduce like persistence, right? And so we got the weighted persistent homology as well, and they try to make applications. So that's good. So remind me like one thing seems this weighted homology will be similar to a delta homology, right? And of course we have joint works with Kelin, and we make applications on weighted homology as well. Seems quite successful. So that's a good tool. And then of course I will think more, and as I will explain, the part for this weighted, I will think about next one, right? Next one, how it will be connected to the some classical theory, as I will explain actually backwards to some geometry. I will say, and there's some classical, I try to change first thing. I try to change this delta as a weight. I want to change it to be twisting. So first step actually we tested to make it twisting. And later in my talk, I will say how it connected to some fiber bundle theory. Okay, So you will see that there's a lot of geometry actually moving in this picture. Now, in this stage, I try to say that when I watch this machine works well for weighted one. Now, what's the canonical way to do? So first step, this is joined with like actually a few years ago, a couple of years ago already, joined with like Rodia Vishina and Jingyan Li as well. So we were proposing the game. Okay, let's assume like a simple complex. Let's make each say each vertex, right? So let's, instead of put a weight up there, let's make some twisting. So let me some endomorphisms. So make a matrix. We just like try to twisting these vertices, and then try to produce some homology theory which it still works. And by checking these laws, and we found that you need a bit of conditions on these twistings. So each twisting, I mean some endomorphism of a group. Okay, so that means each vertex I assign some endomorphism of a group, and well, to make like a law like this, we need like partial is 0, right? Eventually we get some chain complex. So we're checking these rules, and there's some actually there's a natural condition we have to put here. In other words, if there are two, you can put whatever twisting you want, right? Given a vertex, I just put a matrix, I put another vertex, I put a matrix. Now, if you want to make this machine works well, then if there are two, there's an edge join the two vertices. Actually, only one condition. Okay, there's a one vertex, another vertex. If there's a edge join two together, then we need this commuting rule come out. So we have to, and that turns out that the only condition we need. So that's quite interesting. So and mathematically, if some people like working in math, you will see that this kind of commuting rule has some connections with arting groups as well. But of course, I've not moved to that direction. I found this condition seems quite natural. Okay, so that's why we work out this paper, and we not only look at like this introduce homology theory, we put a bit more complicated setting in mathematically. So we look at the non-commutative version as well. So let's in this paper, sometimes people may be hard to read because we are putting in a very general construction. So we make like a free product of groups, and what we call like try to generalize, make a Carlson's construction, so in another way. But now the story still keep going. So in today I'll try to report to you this about like next procedure. Next procedure I'm trying to understand better, so I can move to look at the twistings instead of for each node. I want to twist things on the each simplexes, and then try to look at what's the natural rule we can put over there to make the machine runs well. And then from that direction, and I found that actually eventually we got we can unify the data homology introduced by Professor Yao and classical theory actually introduced on this actually the simplicial version of fiber bundles. Turns out that seems very nice. Well, I should say that the Yao's data homology is quite different. It's not like exactly as what the twistings in classical setting what they said. So it's a new theory, new homology theory. Now we're happy is that because we can unify this how to connecting this data homology with like a classical. Actually, it's very important theory in homotopy theory. It's called simplicial homotopy theory. How to use simplicial way. So in sometimes in discrete way to understand fiber bundles. And so the work, as is indicated, this is exactly the work. The work was well established in this famous paper. So this is given by Barrett Guggenheim and John Moore. They have this is the paper you can see. This published in 1959. Is a title called like on semi-simplicial fiber bundle. At that time, so-called semi-simplicial complex nowadays is called simplicial set. Okay, and these what you can see is a bit like is a generalization of a simplicial complex just by counting degeneracy complexes, so roughly speaking. Now, the setting I put the copy. This is displayed contents is from their paper. So this is so-called the twisted Cartesian product. So of course, in simple set, you see there's a nice settings that the Cartesian product is just in dimension-wise Cartesian product of sets. So it's quite natural construction, and the geometrical realization of that simple set of Cartesian product, still Cartesian product of spaces. And now, interesting part is about making some twisting. So this is what they call twisted Cartesian product. When you do this twisting, actually, roughly speaking, you have all these like these operators, like basis operator, degenerate operator. In one operator, you need some twisting around here. Okay, so that's the game. You make like some automorphisms moving around a bit. And then they discovered that this is a nice model for the fiber bundles. So here's I show you a bit. I just pick up some statement here. So any fiber bundle, you can with some with a group structures, you can will be equivalent to so-called the restricted twist or regular twisted Cartesian product with a group G. Okay, so any fiber bundle can be equivalent, right, to reduce to this Cartesian twisted Cartesian product. And conversely, like the regular twisted Cartesian product in the fiber bundle. So this theory is gives a very nice, at least mathematical, nice description how to describe the fiber bundles in simplicial way. Okay, so in this group. So that's I mentioned like the one classical paper. Actually, there's a famous another classical paper is in 1959 as well. The famous one called twisted tensor products. This is given by Brown's work. Okay, so that's one of his famous work. And as I mentioned, the Brown's work essentially you will see that this is a twisted tensor product is the chain version. So chain version of the previous here's the this is space version by BGM, the twisted Cartesian product on simplicial version, right? Then there's a chain version, this so-called the twisted tensor product, to understand like so-called vibration. So again, so you deal the game with fiber bundles in an even more general setting in homology theory. And here's a bit of information I tell you. So to given a fibrine, you can think about fiber bundle, you will create some co-chain, but a co-chain corresponding to a given co-chain, but this coefficient is not like on a few, it's actually complicated. You have the co-chain with coefficients of the chains on the loop space, so it's a big one. And using this information, actually you can define a twisted this tensor product of chains. So the usual chain complex, another chain complex, you can take a tensor product and define like boundary operators in a way without the tail, okay, without tail. So that's how canonically you look at the tensor product of chains. Now, to understand the fiber bundles, so you have fiber general what is we call like fibrations, and then you can put these tails over here. So as a twisting over there, then the machine will work. That's exactly in this classical work, Brown data. So you see that this work is actually a very nice classical work, did well for understanding a twisted situation in algebraic topology. Now, I mentioned that there's a variation of this for chains. So people, of course, in geometry like to look at the Hahn cohomology, right? The co-chains, and then look at forms of there. And well, there's famous work as well. This given by people maybe know, right? His name called Witten. Okay, so this he actually in 1980s introduced like this twisted the Hahn cohomology as well. With details, you can see that you can have to make some twisting. But there's some, of course, the version slight different as Brown state. What I say from my view, like this is a variations of the Brown's work twisting in 1950s, and of course you move backwards in the space level. The space I mean in simplicial setting level, right? It is reversion theory of simplicial set. You also backwards to like a BGM's theory of twisted Cartesian graph. So that's the historical story about this twisting. And now okay, so now I try to explain like what we try to look at. So this is the, on one hand, we have this delta homology introduced by Professor Yao group recently, right? And in my mind, there's a lot of nice twistings in these classical works. I think the interesting it will be like in Chongqing's conference. I think a few 2 years ago, right? Where I will also explain some, try to understand that how they connected to the classical one. People also ask. Now it turns out now we can work out their connections. So the way where again, so we put our game is try to as general as possible. So we're just starting with a game like we assign, like you say, let's make a twisting for each simplex. Let's say you start with a simple complex, right? So let's make a twisting for each simplex. Then we follow some laws, try to work it out some formulas. So what does it require to make like machine works reasonably? Then turns out here's a general rule, right? Look at a little bit there. So for each twisting, so here's the game is that if you get the so-called what I call like data set. So data set is also called semi-simple set. Now the difference between data set and the simple complex is that the simple complex you get like you have to look at the simplexes. So you get the two vertices can form one simplex, right? One simplex, or you two simplex means you have three vertices. So essentially, once you have vertices are given, then of course they may or may not form simplex. Once they are formed a simplex, they are only at most one, right? So if you give two vertices, say for example A and B, I could possibly have an edge between A and B, but I cannot put like two edges between A and B. That's in the setting of simple complex. You not allow you have two edges to share same like ends, like same node vertices. In the of course general cell complex, you can do that. Now the data set is actually make a game just like different way. So they start to look at the labels. Labels are given by the simplex. So each simplex I give a label. So say for example, I have two edges, right? So first label I can call sigma 1, another label I can call sigma 2. Then from edge, I should have some operators go to their faces. So I can say first phase called D0, second phase called D1. So then, so use like this make simplex as labels and to its faces as a directions as function. So it's actually Hayes diagram of this way to control control like the cells, but still have a natural simplicial notion, combinatorial way to combinatorial properties still keep it. So you can still introduce homology as like a alternating sum of phases for each simplex. So all machine works well. Actually, like in new no, not quite new. I mean, it should be 20 years ago, like Hatch's book of a textbook in algebra topology. Hatch's book already used delta complex instead of simplicial complex for introducing simplicial homology theory. Okay, but that's like a notion of a data set. So if you're not familiar, just kind of generalization of the simplicial complex. And then we just make all this twisting over there, and we found that there's some rules like formulas like that. And well, of course, the game. Okay, well, let me say, I should say more, and I should say that use this. Okay, use this. Actually, we can. There's more stories. Like I don't want to say more. Okay, then use this. I will create. We can create twisted homology. Okay, so for each n simplex, we can make twisting, and then we can use the define the boundary operator in a natural way, and we can also define like in non-commutative version. So we make it so-called simply twisted Carlson construction, like it's twisted simplicial groups, and they give a geometry of loop space. Mathematically, they have some lot of nice property. And important the same one way to try to think about this way. This gives a unification of the delta homology introduced by Professor Yao, and the classical twisted Cartesian product by BGM theory. So it seems I'm very happy we can understand that these very two different games can actually in one picture. And I guess later we'll try to make application this one. Now, here's I want to say a bit more. This is will be joint work with the Guo-Wei and Kelin, like Jelena's work. So this is this work we actually try to try to understand the topological approaches to data science, right? And we try to make some framework, give a framework on this only for mathematical approaches. So, and there's one assumption we try to in here in this work, we try to say we don't want to like you assume like this data already exists distance. So in other words, then we look at this direction. So that's why I call like we try to look at the work on the graph data as our motivation. And then turns out that we can find this, we can unify various topological approach into one picture. And then these approaches can be applicable to both point cloud data and the graph data. So in other words, this point cloud data can be treated in our way is treated as a special case of graph data. So you just take the finite points in Euclidean space, your distance, and then when I treat the finite point as a graph, just to make in a natural way. So you consider as a complete graph. So assume all points have one edge exactly, only one edge joined together. So make it completed. And then you move all games to as the how to study the graph data. Okay, so let's and of course in the point cloud data you also have some distance, and the distance over there we just treat it as some weights or some other information you put in on the edges you give us. And so then we look at the more general situation. So look at the graph data. Of course, you can assume some weight and some additional information, right? So that's our method. And the method actually, then it turns out that we can actually we can introduce a lot of topological approaches when we give a graph data. That means you have you can get many ways to, you can construct many complexes, and their homology could be sharply different. So that means that we can actually, given like one graph data, when we talk about topological feature, actually then turns out you have to see which homology you apply, because you could have get different where through different views you can construct different complexes. You may produce different homology, so you get different topological feature. And now then there's you make this game as general as possible, and turns out if you give a working graph, and whenever you give select any collection or subgraph without we assuming like you just start with select any collection or subgraph without constraint much. Essentially, you need a little bit of constraint condition, like you have some directional phases once you give. Just as a minimum as possible constraint condition on the collection of subgraph, then we will be get homology theory. So your homology will come out in the natural. So in this case, of course, we still have got some what we call the topological invariance. Now, this topological invariance, the complex of this collection of subcomplex may or may not be a real complex. It means they may not be simple complex or even cell complex. So what I call like this kind of geometry like. So they're kind of structures. So we can then we still have homology. The key point, the homology theory still works. So that means we still can get topological feature, right? And another thing for solving this persistence. So if you look at the classical TDA, there's two important things. One, you need to get Beatty numbers. So that means that you need a kind of homology theory to understand these shapes, whatever you constructed, right? In that case, actually, there's a real geometric shape of that. Now, in our setting, because we put in a more general situation, we make a geometry-like object, and because timings I showed, so geometry-like object, but we still have we can think about kind of shape here, and then we can use scoring scheme. Once you give a working scoring scheme, you get filtration. Once you get filtration, of course, you get persistent. Then once you get persistent, then you get Beatty number. You will get like persistent barcodes, and you get topological feature, and then you put the machine learning. And there's another amazing point is that in this framework is that actually we can come back to let me try, so we can adjust it because you get a already general method. If we think about this collection of subgraph is not so good, let's make some changes. So in other words, we can make some learning out of that. So we can adjust it. And then we improve the score. And then we try to continue. So we hope later on we try to make it like these topological approaches to start with any randomly choose some collection subgraph, then we try to aim into like better and better, and then we get some nice proper topological feature which can fit well with the working graph. That's a hope. So here's some information. There's a notion called super-hypergraph, actually, which that's a generalized the hypergraph as well. We have a generalization in this article introduced one, and there's a lot of complexes. Actually, we look at the graph data, you will see that a lot of clique complex people usually use it, right? In addition, there's a famous one as well, neighborhood complex. That's the foundational notion in topological combinatorics. And if people pay attention more, there's some Johnson's graph complex, which is given by H1. And also the path complex given introduced by Professor Yao. So you see a lot of games. Now, because timing, I should stop here. Okay, thank you very much. Okay, so I should ask any questions on the. Yeah. Yeah. Okay, so now, yes, now I should, so I finished my talk. It's actually, I chair myself, right? So any questions, comments, please ask. Yeah.
Yeah, maybe I have a question. So for the twisted homology, how is the computational cost compared with the other homology? Do we need to tune in the coefficients from Z2 to Z, or how is the computation?
Okay. Yeah, so actually, as I said, so far, the twisting homology, I'm still mathematically curious for this one. There's an interesting part that I ask the student to look at look at the usual homology. I say testing for these games. So let's try to take a coefficients with, say, Z plus Z. No, usual homology, let's look at the integral homology. So the integers, right? So let's try to make like a coefficient group to be like a Z plus Z. So we get the, like a vector space or two-dimensional vector space. Now, twisting will be like, you just assign 2x2 matrices as twisting, right? So for fun. And actually now there's a lot of funny twisting you can put, like you say, use SL2Z. You look at this, there's some interesting matrices which in number theory, you can see what happens. So I think there's some testing. I think Meng, okay, I should say that. This is Meng is working a lot. She did quite nicely on this topic. So she make example. The output of homology is very different from the usual one. If you make your twisting in a very strange way, and the output is really different. So it is clear that it will give a new homology here. Now the cost so far, because we have not moved to really computation, so we just say testing simple case for by pair, see what happens first. Later we will see simplification and balance. Yeah.
I see. Yeah. Thank you. Yeah.
Yeah. Okay, so now let's see any more questions. Now I can stop sharing, right?